Okay, good day, everyone. So here is the question, what was the exercise that I gave you. Now, we are told here that this is the graph that we are told, the direction graph here. And the first question was, what is meant by the term, what is meant by the activation energy of the reaction? And I think all of you got that correct. That is the minimum amount of energy required, for the reaction to take place. Okay, so now that activation energy is required to break the bonds bonds in the reactants. Okay, so it's required to break the bonds in the reactants, because you can see that we have got A, B, but it has to break. We need to break the bonds between that. Now in that process, we'll form an activation complex. Then let's see what the question is saying here. Determine the activation energy of the reaction, and on the graph. So in question 2 here, this is what we have here. We have got the activation complex, activated complex. So activated complex, or we can call it the transition state. Okay, or intermediate, or just the intermediate, because it's between intermediate. Okay, now here what we have here is that we are told that determine activation energy. Now activation energy, which is your EA, okay, you must always remember that, is equals to the activation energy, the energy for the complex, the activated complex. Okay, the energy of the activated complex here, that's what we have here, minus the energy of the of your reactants. So always remember that your activation energy is from your reactants. Okay, it's from your reactants. So this was supposed to be your your EA. Okay, it's always started from the reactants. So in this case, you can see that activation energy is between EA. And if it was, maybe, let's say, if it was like this, maybe like this, yeah, like we have got products with more energy. Okay, it means that our activation energy, we're supposed to stand from there to here, ways down, because you can see that here is below the products have got less energy, but here the product reacting that one with less energy. So this was supposed to be your EA, like that. So always know that that's what we have there. Okay, now so here we just supposed to estimate here. You're supposed to estimate. Okay, you're supposed to estimate here what is it here, because between 40 and it's actually slightly below. So you can just use 43, minus 20, which is for the reactants, which you get kilojoules. So always remember to include the units. Okay, then what is represented by the X on the graph? Remember, X is representing the activated complex. Okay, we've done that. Now determine the heat of reaction of this reaction. Heat of reaction, guys. Heat of reaction is the same as what? Enthalpy of reaction. Enthalpy change, isn't it? Enthalpy change. So enthalpy change. So you must always remember that these two are the same. And you know that enthalpy change. How do you get enthalpy change? You say enthalpy of what? Products. Okay. Enthalpy of products minus the enthalpy of of reactants. Okay, of reactants, of which here you get what you're supposed to get is 10 minus what? 20. Okay, because you see that here the products here is actually having 10. The products here are having 10. Okay, any enthalpy of 10, and the reactants are having 20. So it's actually 10 minus 20, and you get negative 10 kilojoules. Okay, now here the third question here is saying, so this question is saying what, is this reaction exothermic or endothermic? So this reaction is actually an exothermic. It's actually an exothermic. And remember what we said when it's an exothermic. exothermic reactants. Reactants will have more energy. Okay, we have more energy. Reactants have got more energy than product. That's what we say, and that's why it's an exothermic reaction. Okay, now what effect will the addition of a catalyst have on this reaction? Use a graph to illustrate the explanation. Remember this now. We know that catalyst, what does catalyst does? Your catalyst, offers a pathway, so it lowers activation energy. So your catalyst lowers activation energy. So if we are to come to our diagram here, we'll expect something like this, okay? We'll expect something like this here. So we are saying this is the graph without a catalyst, okay? But now, with the catalyst now, we'll expect a lower activation energy. We expect a lower activation energy. So here now, you can see that the EA that we have here is no longer the same. So here, so this is our new EA from the the previous EA, where we are starting from X. So here, this always know that your graph of a catalyst is below the one without a catalyst. Always know that. Why is it like that? Because of the activation energy here. Okay, so you must know the impact, of adding a catalyst. So this was supposed to be a graph, guys, and I think I have added explanation on how the catalyst affect your reaction. Okay. Okay, I think I've left out something here. We're saying describe the structure of X in general terms. So your X here, remember we said it's an activated complex, and this is a group of atoms. Remember here, the atoms are bonded together, and the bond breaks. After the bond breaks here, it forms it forms free atoms. So here, actually, this is an unstable. So most of you were actually stating that this is an unstable transition state, which is actually correct. But now you must also add that transition state. Now add also that we have got free atoms here, group of free atoms here, group of free atoms. So here they are not bonded together here. So free atoms that are actually there. Then now it's actually in the process of forming products. Okay, so new bonds now will stabilize the X, and you know that in the products we form new bonds. So here activation energy is required. It breaks the bonds in the reactants. After that, activated complex forms, and the activated complex it's a unstable, it's a transition, and it consists of free atoms, and those free atoms will now bond together to form a stable state of your products, which is A plus B in this case. Okay, so don't forget that. Now let's move on to question 2. Okay, it's saying now a mixture of gases, chlorine and methane, will not react spontaneously. Okay, however, once the mixture is placed in the sun, okay, a reaction will take place over time. Explain why this is so. So remember, we have got what called endothermic reaction and exothermic reaction, and you know that. Now, in this case, this actually shows that this one is an endothermic reaction, because the molecules on themselves, they don't have enough energy. So what happens is they need energy, so for them to react. And according to collision theory, okay, your molecules can only collide when they have enough kinetic energy. Now here, gas particles do not have required minimum kinetic energy. Okay, here's the answer now. Okay, so which is your methane and chlorine, which is equal to the energy, which is equal to activation energy. So they can't collide. So therefore, no collision occurs between them, between chlorine and methane gas particles. Now, when placed on sunlight, okay, chlorine absorbs heat and form radicals. So when you're talking of radicals here, we are saying chlorine, you must know the formula of chlorine. It's 2, and this one here is stable. Okay, it's stable. And when it forms radical, when you apply heat now, okay, when you apply heat, you form radicals. So radicals. So in this case here, these two are unstable. So here, these are unstable. So here, they're actually willing to react. So in this case here, they will require less energy in this case. It requires more energy for this one to react than this now. When it's a radical now, it can quickly react with what you call methane. And the methane, you must know methane is CH4, sorry. So it's more like CH4 like that, okay? That's what you call methane. And one of the hydrogen here is replaced by the what? By the what you call the radical. So if we add these two, we'll now form what you call what you call here Cl H plus HCl, which is hydrochloric acid. So one of the H will react again with what? With the chlorine here. So that's what we need to understand here. Okay. So that's what you call for number 2. So these two will only here after chlorine absorb the heat, form radical which require less activation energy to react with methane to form what you call methyl chloride. So like what I said now, effective collision can now take place, can actually occur now, and reaction take place. Okay, so that was number 2 here, question 2. Let's move on to question 3. What was question 3 saying here? So question 3 is saying what you call the collision theory can can be used to explain how different factors affect the rate of chemical reaction. Name 2 conditions that determine whether a collision between the 2 molecules A and B will lead to a reaction. And we know that here, your particles must have enough what? So this was 3.11, okay? Must have enough EA, or what called EK, which is what called kinetic energy. Kinetic energy. So enough kinetic energy. So they need enough kinetic energy for what called for collision. So for them to collide, colliding particles must have enough what called kinetic energy. Most of you are just stating that colliding, they must collide, yes, but they must collide with sufficient kinetic energy. So the main point here is particles must have sufficient energy. They must collide, yes, but they must have sufficient energy. Number 2, they must collide at right orientation. Because remember what I was explaining to you, that without the right orientation, particles orientation won't take place. So it must be right orientation. Most of you just stating orientation. What about it? So we need to actually say that it should be the right orientation. Okay. Now the question, the question in terms of the collision theory, explain why the rate of chemical reaction increases what you call with increasing temperature. Now, when you increase the temperature, what happens now when you increase the temperature? When you increase the temperature here, increasing the temperature, what you call increases what? Kinetic energy. So here, increasing temperature increases kinetic energy for particles. Now here, once you have got high kinetic energy here, once the kinetic energy is increased, so increasing temperature increases what? Increases kinetic energy of particles. Okay, so now increase the kinetic energy of what called of particles. Now it means that when the particles have got more energy, so it means that more particles will collide effectively. So here you must know that effective what collision will collide effectively. So when you are saying effectively, what you call effectively, so effectively it means that it will result in a reaction. So effectively, okay, what you call per unit time. Okay, so effectively per unit time. Okay, leading to a reaction. So particles need kinetic energy. When they have got kinetic energy, more particles now will collide because more of them are excited now. They are having energy. Now, when they collide, they are probably going to collide effectively. And when they collide effectively per unit time, what happens? They lead to a reaction. That's according to the collision theory. Okay. Now, the second question here, what is it? 3.2. Okay, so 3.2, the relation between nitrogen dioxide and carbon dioxide is presented below. Okay, these are relation that which you see, and we can see that your what called enthalpy change here is what called is negative 26 kilojoules. Okay, now the activation energy for the reaction is what 132, and you know how to get activation energy. Now here, what is it? Sketch a potential energy versus cost of reaction. Okay, graph for this reaction. Label the axis and indicate the following on the graph. So you must label the graph, meaning your potential energy, your reaction, course of reaction, and also you must indicate these two. You are done. You get your marks. Okay. So this is what you see here. You find that here is potential energy here. Okay. Here is your course of reaction. Those are just 2 marks for you to take. Now they are telling you that what is it? The enthalpy change. Sorry, let's start with the activation energy. Activation energy. Remember, we said from the maximum to the reactance. From the maximum to the reactance. That's what we are having here. Maximum to the reactance. Okay, to the reactance level. Okay, that's the activation energy. From the activation complex to the maximum to the minimum, to your reactance here. Now we get 132. That's the activation energy. Now the enthalpy change here. You can see that here is what? It's what you call, it's negative 226, and the enthalpy change is between your product and your reactants. Product and reactants. That's the enthalpy change. Activation energy is between your reactants and the maximum, number 1. Now, they are saying what you call, use a broken line on your graph to show the effect a catalyst would have on the potential energy on the reaction as the reaction proceeds. Now here, remember what I said earlier on, your catalyst lowers activation energy. That's it. The graph with the catalyst is below the one without a catalyst. Simple like that. You must always remember that, guys. Okay. Now let's move on to question 4. Now question 4 is saying a learner investigates a method to increase the rate of which hydrogen gas develops in a reaction between zinc and hydrochloric acid. By changing one of the reaction conditions, she obtains accompanying graphs in which curve X represents the original curve, the curve Y represents the change condition that results in a higher rate of reaction. Now here is the first graph here, okay? And you ask that which reaction condition did the learner change, and what was the direction of the change? So here we want to see the graphs here that you're seeing here. So what you're seeing is that these 2 graphs here, we have the original graph, which is your X, and we have the other one, which is your Y, which is the condition. Now, as you can see here, we have got more particles that are now having more kinetic energy, because this is a kinetic energy. We are increasing kinetic energy. Okay, it means that less particles here, their maximum of here, more of the particles have got less kinetic energy here. But you can see that now our average our average EA here, EK, is actually increased. So what probably would be that? It should be temperature. So when you increase the temperature, temperature. So temperature here, when you do this, it means that temperature was increased, because when they say state the change can be decrease or increase. So here temperature increased. So when the temperature is increased, we have got a large portion of particles that are having your EA, which is what we call above this is your EA here, what you call activation energy. And we are saying more particles now in this case here, you've got EA or kinetic energy above EA. You understand? So here, these particles have got EK above EA. You understand? That's what we have here. So we can see that we've got less particles for the original graph, which is X, but now we've got more particles when we add temperature. Now, so here you can see that when it's shifted, when your graph is slightly shifted here to the right, you know that, oh, that increase is called increase in temperature. Now, the second question was, apply the collision theory to explain why the change condition lead to a higher reaction rate. So here, I'm just going to read for you here because you know what's happening here. At higher temperature, more molecules move faster. Now, when they move faster, remember what I said, they're having more kinetic energy. You add more what you call it, increase the temperature, you increase kinetic energy. Now here, more particles have got higher EK. EK is your kinetic energy. More particles have got the kinetic energy above your EA, which is your activation energy. Now, more effective collisions now per unit time between the particles, and thereby what you call increased rate of reaction. Now, here, effective collision, you must understand this term here. Effective collision, collision that leads to a reaction. Okay, that's what you must know. Now, what you call the second question here, she then changes another condition. The effect is represented in the graph, in the following graph, in which once again curve X, okay, curve X represent the original, and this one represent the outer one. Now, as you can see here, let's look at this. But now we can also see now that this is about a catalyst. Once you see a lowered activation energy, you know that, oh, that one is a catalyst. You mustn't think twice then. So these are the graphs that you must actually look what you call and understand now, so that in preparation for your exams. Now, which reaction conditions did the learner change? In this case, we know that it's a catalyst, okay? It's a catalyst. So a catalyst 4.2 is a catalyst here. Now here, catalyst added, okay? Catalyst added. So here it was added. Now here, name the energy values that is represented by P. Now, if you look at P, remember, P is your, this is a difference in what? Difference in what? In your enthalpy change of products and enthalpy change of reactants. So this is a heat of reaction. Heat of reaction or enthalpy change. Enthalpy change. Remember, these mean the same thing, enthalpy change or heat of reaction. Now, what about Q? Let's look at Q here. At Q here, Q, most of you are getting this correct. This is activation energy. Yes, activation energy. But now, what about it? Because the R also is activation energy. So activation without a catalyst. So you were supposed to specify here that there was no catalyst there. What called activation energy without a catalyst. Then with R is activation energy with a catalyst. Now, lowered activation energy is the one with the catalyst. Now they're asking us draw a Maxwell-Boltzmann what you call distribution curve to show the effect of this change. Now, here is your graph here. Now, in your graph here, you must understand that your Maxwell-Boltzmann is actually number of particles, okay? Number of particles that are having a certain kinetic energy. So number of particles with given kinetic energy. Now, when you add a catalyst, you are increasing the number of particles. You're increasing what? Number of particles with EK. With the proper what called with so you're not increasing number of particles, you are reducing activation energy. We know that the former activation energy is here, but now when you add a catalyst, it lowers activation energy. So catalyst lowers activation energy. You must master this, guys. You must master this. A catalyst lowers activation energy. So you must know that when you see an activation energy, it's actually there are two activation energy. You know that, oh, I got you. That's a catalyst. Okay. Now here, so the last one, yeah. So here, a larger number of particles, you have got what called EK over, which is kinetic energy over EA. Okay, because EA for the reaction, what called reaction with the catalyst is lower. The EA for reaction with the catalyst is lower. So I hope you guys you understand and enjoyed your lesson. Okay. Until next time, thank you.